Okay, so all right, so now let's go forward with the next part of this chapter, AC to DC converters, which is full wave, uncontrolled and controlled AC to DC conversion, single phase supply. We'll be talking about these AC to DC converters for pure resistive load and inductive load, also called RL load. And we'll also be discussing about continuous and discontinuous current modes when we are dealing with the inductive load. But before going further, I need to make sure that some of the concepts which we'll be dealing with in full wave rectification are already discussed in half wave rectification. And most of these concepts are discussed in detail in half wave rectification. So it's a kind of a prerequisite before going into the full wave. So you have to understand by going through these lectures for half wave, so that the terms used in full wave needs to be understood. Okay, so let's start with some basic overview on uncontrolled full wave rectifier for pure resistive load. By uncontrolled, I mean to say that if we have a thyristor circuit and we have a firing angle alpha equal to 0, so this particular rectifier is now working as a uncontrolled rectifier, just like the full wave diode rectifier. So that's what we'll be discussing, having quick overview on this one. So assuming all thyristors having a firing angle of alpha which resembles a diode rectifier. Okay, so to quickly go through this one, again we'll be working in two modes. One is mode 1, where we are talking about the positive half cycle of the input supply over here, which is a sinusoidal input AC signal. And mathematically, we can describe this sinusoidal AC signal as Vm sin omega t, as we know since our first lecture. Okay, in the positive half cycle in mode 1, the top terminal is positive compared to the bottom terminal. So the current starts to follow this direction, shown by the red arrows over here. So the E1 will get forward biased and the current starts to follow this path. Will not go here because D3 is now reverse biased. So we'll follow this path from top to bottom through this resistive load, and then going back to the source through this D2, and then going back to the negative terminal of the source. So from here we can say that, assuming these diodes to be ideal, so no voltage drop across these diodes, so whatever we have at the supply part, the positive half cycle is completely appearing at the resistive load at the output, which can be seen from this waveform. So V out, voltage at the load, the resistive load. So exactly this positive half cycle is appearing at the load. Now in the negative half cycle in mode 2, the negative half cycle, now this bottom terminal is more positive compared to the top terminal, so the current will follow this path. So the current starts to flow from here like this, going through this path D3, because D2 is reverse biased, so it will follow this path, going through this, and then again going from bottom to the top through this load, the same direction which we saw in mode 1, and then going back to the top terminal to complete the path. So Again, the same half cycle is appearing at the load without any voltage drop through the diodes, but reversing in polarity, because at the load it is following the same direction from top to bottom. So if the current is following this path from top to bottom, this is positive compared to this one, as we saw in mode 1. So at the load, the direction is again the same which was in the positive half cycle. No matter at the supply side, it is reversing its polarity, but at the load side, it is following the same direction, which can be seen from here. So in the negative half cycle also, we have the same voltage polarity at the load. It means that we have two pulses in one complete cycle from 0 to 2 pi. So from 0 to 2 pi, we have two pulses at the output. So we call it a full wave rectifier. In half wave rectification, from 0 to pi, we have a pulse at the output, but we do not have any pulse at the output from pi to 2 pi. So it was a one pulse rectifier. So this is a two pulse rectifier and using diodes or using thyristors with alpha equal to 0. Similarly, this current over here, the load current, also following the same direction in both the modes. In the positive direction, positive half cycle of the supply, it follows this direction, and in the negative half cycle also, it follows the same from top to bottom. So just by looking at this, we can say that now we have converted this half wave rectifier into a full wave rectifier just by adding these diodes in a bridge configuration. So we have two pulses per cycle from 0 to 2 pi. Similarly, as we saw in half wave rectification's case, that these ripples now, which we are seeing here in voltage waveform and in current waveform, can be removed using a capacitive filter connected in parallel to the load, which we have already discussed in details in half wave rectifiers chapter. Okay, so now proceeding further with a controlled full wave rectification again for pure resistive load. Now the same circuit, but now we do not have this firing angle equal to 0. It is greater than 0. So again, we will be working in two modes, mode 1, which is positive half cycle, and mode 2, which is negative half cycle. So again, positive half cycle is from 0 to pi, and negative half cycle is from pi to 2 pi. So when we work in positive half cycle in mode 1, so this again, top terminal is positive compared to the bottom terminal, and the direction of the current will follow the same route as we saw in the previous slide. The only thing now is that these thyristors are now triggered only after some angle which is alpha greater than 0, which is shown here in this waveform. So let's say this thyristor is now triggered over here at some angle alpha. Before this angle alpha, there is nothing at the output because the thyristors are off. All the thyristors are off. So this supply is now not connected to the load, or it is disconnected from the load due to the reverse biasing of these thyristors. So we do not see anything at the load. So zero value of current and zero value of voltage at the load. As soon as we trigger this thyristor group, again the same T1 and T2 during the positive half cycle or mode 1, these T1 and T2 are conducting, and the direction of the flow of current is again from top to bottom through this load, and now the path is complete. This at angle alpha, T1 and T2 are triggered, they turn on, and the load current starts to flow. And now due to the flow of this load current, we have a voltage drop or voltage at the load, which is shown by this waveform. So the current starts to follow and the voltage also starts to develop at the output. So we have a clipped output from 0 to alpha. So from 0 to alpha, the output is clipped. So from when alpha is above 0. So in that case, the average value of the current is lower compared to the previous case when alpha was 0. If we keep on increasing the value of alpha, the average value of voltage and current will be lower. So just by adjusting or changing the value of alpha, we can change the output voltage and current. So these are the analytical equations for the waveforms we saw in previous slide. So to mathematically write down these expressions, we can just use the same concept we saw in half-wave rectifications case. So this is the instantaneous voltage, Vm sin omega t, from alpha to pi, because omega t continues from 0 to infinity, but from 0 to alpha we have 0 output, so no need of writing this. So from alpha the output starts to develop at the load. So from alpha to pi, we can say we have one wave at the output, so one pulse at the output. So this complete instantaneous voltage is developed at the output from alpha to pi, integrating the complete instantaneous voltage divided by the total base. In half-wave rectification case, if you remember, we have one pulse per complete cycle, which is 2 pi. So the total base was 2 pi having one pulse. But from 0 to alpha to pi there was output, but from pi to 2 pi there was no output. So the total base was still 0 to 2 pi. In this case, we are having two pulses per 2 pi of the cycle. So 2 and 2 will cancel out. We have one pulse per angle pi. And integrating from alpha to pi, we have this average value, which is Vm by pi 1 plus cos alpha. If alpha is 0, we have an uncontrolled full wave rectifier. So then the average output, which is a DC output, will be Vm by pi multiplied by 2, 1 plus 1, 2, cos 0 is 1. So 2 Vm by pi is the fixed average voltage at the output. So if we have some angle alpha, which is firing angle, then the voltage will keep on changing this depending upon the value of alpha. Again, RMS value also the same, squaring it, then taking an average from alpha to pi, dividing it by the base pi, taking square root, we have RMS voltage. Dividing it by resistance, we have RMS current. And then we can get easily this power value over here, V square RMS divided by R, or I square RMS multiplied by R. So very simple, similar to the half-wave rectifier. So this is one simple exercise you can do. So a rectifier, a bridge rectifier having a delay angle of 40 degree, voltage supply 120 at 60 hertz, 20 ohms is the load, and then we need to find out the average current and power. So this is the average voltage, Vm by pi 1 plus cos alpha, we saw in previous slide over here. We get 95.4 now the volts, and now current is this output voltage in DC divided by R. We have this current, and we can easily find out RMS current from this RMS voltage. We can find out over here like this, dividing it by R, we have RMS current. So we have this RMS current of 5.8 amperes, and using this we can get power. So this active power is 673 watts, and using this active power and apparent power is Vrms multiplied by Irms. It is this 696 volt amperes, and using this active power and the apparent power we get power factor, which is active power divided by apparent power. It is 96%, 96.7%. So we know that for pure resistive load we have 100% of power factor, so it is quite close to this 100%. Okay, so now moving to the RL load, if we have inductance at the load. Again the same thing, during the positive half cycle, we have T1 and T2 triggered, just we saw in previous slides. But now the only thing is we have inductance involved in the output load. So when we go for the mode 1 for positive half cycle, these T1 and T2 are forward biased, but they are not turned on at the moment. They get turned on when we have a gate trigger applied. So now the gate trigger is applied at some firing angle alpha. Now the load current starts to increase slowly, like we can see from here, in some finite time. And now this supply voltage is appeared at the load because of the turning on of these thyristors, T1 and T2. The circuit is complete through T1 from the positive half cycle at the top through T1, and then through load from top to bottom. The current keeps on flowing through T2 and then back to the source, just as we saw in the previous case. So the voltage starts to develop at the load and the current slowly starts to develop. Now, due to this inductive load, the increase in this current is very slow, means depending upon the value of inductance. Gradually it increases, not abruptly, as we saw in half-wave rectification case. So now energy starts to get stored in inductor, starting from angle alpha, where the thyristor starts to conduct, as we can see from here. From alpha till this current position, we can say now the current starts to develop. Now at angle pi, the current reaches the maximum point, and now the supply voltage reverses, as we know that at after angle pi we have a mode 2, means negative half cycle. So mode 1 is finished now, as in the case of resistance or resistive load. So at angle pi, the voltage reverses, means now the bottom terminal becomes more positive compared to the top terminal. But the thyristors keep on conducting, both the thyristors, they keep on conducting, because due to this inductance, the current cannot be reduced to zero. Similarly, we saw the same thing in half-wave rectifications case. So the current reaches maximum at angle pi, and now the inductor is energized. Now, after angle pi, the inductor current starts to decay. The reason is because now at angle pi, the supply voltage reverses itself, but due to the presence of inductance, which reverses its polarity, these thyristors keep on conducting. So the energy stored in the inductance is dissipated through this load, and part of it is fed back through these thyristors, and now the current reaches zero. When the current reaches zero, that point is called beta. When full energy stored in inductor is dissipated or is consumed, the current reaches zero. This is called angle beta, which is extinction angle, where the current extends to zero. Now here the thyristor T1 and T2 gets off or turned off. So the thyristors T1 and T2 are turned off, and now the new cycle begins where mode 2 starts, and T3 and T4 are now triggered in the negative half cycle. Because all the energy is dissipated from this inductor, the current goes to zero. Now the new cycle starts, and this negative polarity will continue to conduct this, make this diodes, make these thyristors forward biased. And after the next trigger, these T3 and T4 are turned on, and the same cycle repeats itself. And this type of waveform is shown at the output. Like the same, it grows to the maximum value, goes to zero, grows to the maximum value at angle pi, goes to zero and at angle beta, and then the next cycle starts from here. So now, based on the flow of current, we have two modes. One is a discontinuous mode, another one is the continuous mode. So let's say discontinuous mode over here, the current rises and then goes to zero at angle beta, as we saw in the previous slides. And after angle beta, a new trigger for T3 and T4 is done. So from alpha to pi, T1 and T2 are turned on, as we saw in the previous slide, which is mode 1. Or in other words, from beta till pi plus alpha, the current remains zero until the next T3 and T4 are triggered. So that is what that beta to pi plus alpha, the current is zero. That is called discontinuity in current. So we call it a discontinuous mode of conduction of this circuit, because the current goes to zero for some time. It loses its continuity, as we saw in half-wave rectifier. The other mode is the current does not go to zero, because we know that at pi plus alpha, we apply the next trigger. At alpha, we apply the first trigger to T1 and T2, and at pi plus alpha, we apply the next trigger to T3 and T4. And in continuous case, the current, the load current, does not go to zero before pi plus alpha, as in the previous case for discontinuous current. So what are the conditions that decide that when the current will go to discontinuous mode or in continuous mode? So in continuous mode, we do not have angle beta, because it never reaches to zero, the load current. So in that case, first of all, the same current equations you need to remember, which we derived during the half-wave rectification study. Same from alpha to beta, this is the load current, and this is the impedance, and the phase angle, and the time constant. So from this alpha to beta, we have this much current for discontinuous case. So it means beta should be less than alpha plus pi. This is alpha plus pi, means when the next group of thyristors is turned on, T3 and T4 are turned on. So before T3 and T4 are turned on, this beta should be less than pi plus alpha. That is the first condition for discontinuous mode. So at that time, as we saw in half-wave rectifier's case, exactly the same, that current is zero. and we can use this expression to find out the value of beta, as we saw in the half wave rectifiers case. So putting the previous equation 4.18 to 0, we get a value of beta. So for continuous current mode, current should not be 0. So this IB should not be 0, or that 4.18 should never be equated to 0. It should always be greater than 0. Continuing with the discontinuous mode, using that expression from 4.18 for that current, and then subsequently this voltage, instantaneous voltage, the supply is Vm sin omega t. From alpha to beta, dividing it by angle pi, we have this Vm by pi cos alpha minus cos beta. And then similarly, average current is dividing it by R. This VDC divided by R. We have that average DC current at the output. Same is for the RMS voltage as we saw previously. So now after this discontinuous current mode, which we saw from here, this once you fulfill this condition, you can find out the values of voltage, DC voltage at the output, DC current, RMS voltage and current at the output. Now let's say this current at pi plus alpha must be greater than 0, which is solved over here. So this alpha is now less than equal to this value. So after fulfilling this condition, we can solve the DC output over here. Whatever is calculated value of alpha over here, we use the same alpha value over here. So the thyristors must be triggered with condition 2. So thyristors need to be triggered at value of at angle alpha, fulfilling condition 2. So it means we need to decide the values of L and R to operate this rectifier in continuous current mode. So this will be the waveforms for continuous current mode when L is far greater than R. Same concept we saw in half wave rectifier. So if we want to remove these negative voltages at the output, we saw that in rectifier's case that it does, the thyristors does not stop conducting at angle pi. They keep on conducting after angle pi till angle beta or pi plus alpha in continuous conduction case, or in discontinuous conduction case till angle beta. So how to get rid of this negative voltage at the load? We use freewheeling diode, the same we saw in half wave rectifier. Just by using the freewheeling diode, we can get rid of the negative voltages at the output and making inductance much larger compared to resistance. So making time constant much larger. L by R is large. So time constant is large. If time constant is large, the smoothness increases at the output. The ripples get decreased at the output. This is one example that we can solve easily. Same 120 volt RMS at 60 Hertz. R and L values are given, firing angle given. We need to find out the load current. We need to find out the expression for load current. So we can calculate the peak value from the RMS. We can calculate the impedance from R and L values. We can also find out the phase angle from L and R value. We can also find out the omega t value over here. Now, using that expression in 4.18, we can find out the value of beta by solving this 4.18 by substituting current at beta equal to 0. This equation at beta equal to 0. So beta is calculated using this expression, as we saw in half-wave rectifier's case, which comes up to be 216 degrees. So in this case, pi plus alpha, what was alpha? 60 degrees. Pi is 180. So 180 plus 60 is 240. So in that case, we can see that pi plus alpha is larger compared to beta. And we saw in discontinuous current mode case that pi plus alpha should be greater than beta for this current, for this discontinuous mode to happen. So in this case, we can see that pi plus alpha is greater than beta. So in looking at this condition, we can say that this circuit is now working in discontinuous mode. Same we can easily find out the DC current and the power. And the limits always we know that for discontinuous mode is from alpha to beta. All these things I have explained in details in half-wave rectifier's case. Uncontrolled full wave rectifier case or controlled full wave rectifier's case, we can, on similar terms as we did in half-wave rectification, using Fourier series, we can easily identify the harmonic content using this Fourier series. And this we already know, this is the DC component, and then the harmonic component superimposed on this DC component. And as I explained earlier, that we always need to check whether any harmonic content is being superimposed on the DC component or not. So this is what we want, the DC component. But these are the unwanted harmonic content already superimposed on the DC value at the output. So, as I said earlier, first step is to evaluate what harmonic contents are available in the DC output, and then how to get rid of this, or whether to get rid of these or not. So using these equations, we can identify the harmonic contents based on the value of n. N can give us the harmonic components. If n equal to 2, it is the second harmonic component. N equal to 3, third harmonic content, and so on. So this, the DC component, this is the harmonic component of the current superimposed on the DC component. And from here we can say that as we increase the value of L, the harmonic value of current will be decreased. So it means, as we saw earlier in this lecture, that if we have a large value of L compared to R, the current becomes continuous, the ripples reduces. And same way over here, if ripple reduces, it means the harmonic content reduces. So increasing the value of L will decrease the value of harmonics. So in that case, L is much larger than R. Then this instantaneous current will be the average DC current, means no harmonic components. If omega L is made much larger compared to R. So in our design, we need to have a bigger inductor if we want to have lesser harmonics, but it becomes costly. So that's why other design techniques need to be used. Said, okay, either go for the big inductor, and automatically it will reduce the harmonics and ripples and losses, because harmonics means losses. They consume power, unwanted losses. So this is one way of doing it. And if you say we cannot spend too much money on having a huge inductor and other problems also associated with the huge inductor, then the second option may be to use design techniques, elegant design techniques, to filter out the harmonic contents in the circuit or at the load, and use some circuit techniques like filters and so on. So, okay, from the previous slides, these are the approximation if the inductance is of very large value. So then no harmonic contents and only DC component. So this is an example for to find out the harmonics. So these values are given for RL load. We need to find out the average current and the first two harmonics. So average current can be found out. So we have 0.64 amperes, and the first two harmonics for n equal to 2 and 4 means second and fourth harmonic. And second harmonic has a voltage of 42.4 volts. Fourth harmonic has a voltage of 8.5 volts. And if we find out the currents using these voltages, we can find out the current. So the second harmonic has 0.42 amperes of current, which is kind of close to the actual DC current we want at the output, 0.64. So this harmonic content can cause a big problem for the load current over here. So this can be removed. The first option, as I said, increase the value of L. So if you increase the value of L, this value will be decreased. Other one is that, okay, don't touch upon the value of L. Use other circuit techniques to get rid of this, like filter. Remove this using filter. The fourth harmonic has a current of 0.08 amperes, which is kind of negligible compared to the DC component. May not cause any problem at the output, may not cause any disturbance or noise at the output. So this can be neglected depending upon the type of application. If the application doesn't allow any discrepancy or any disturbance at the output, then this harmonic content, no matter how small it is, must be removed. Like in MRI imaging. So even a small disturbance can give us a false result at the output. So in that case, this even a small value of current can be removed. So depending upon the application, these things are normally decided. So now continuing further for three-phase, we'll go quickly through this. For three-phase, we know that we have three-phase supply over here. Here it is shown three phase currents over here, IA, IB, and IC. So three phase voltages, AN, BN, and CN. So AN means a voltage, phase voltage with respect to the neutral. Phase A with respect to neutral. Voltage across phase B with respect to neutral. Voltage across phase C with respect to neutral. And then this three-phase supply is connected to this diode bridge. These. And then these three-phase voltages are Vm sin omega t for the first phase. Second phase, it is this, you can say, it has a displacement of about 120 degrees. And third one is also having a displacement of 120 degrees. So all the three phases are 120 degrees apart from each other to cover 360 degrees, 2 pi. So this is the load connected at the output of this bridge. And why we go for three-phase rectifiers? The reason is that they give us a higher value of DC output. And if we get a higher value of DC output voltage, we also get a higher value of DC output power. Means then we get a high power rating at the output. We can operate higher voltages or higher power rating machines at the output. So the voltage, this ripple frequency, that also becomes higher. So in that case, these ripple frequencies become higher, then we can say that RC constant can be adjusted. So if ripple frequency becomes higher, the RC constant can be decreased, or RL constant can be decreased. So it means the size of inductor can be decreased, or value of inductance, as we saw in previous case for full wave rectifier, we need a larger value of L to smoothen out the ripples. In this case, the demand for higher value of inductance can be minimized. Filtering requirements are simplified. Yes, of course. If RC constant becomes smaller or LR constant becomes smaller, so filtering also becomes easy. So small components can be used to design a filter, and high frequency ripples can easily be removed. So these are the benefits if we use a three-phase rectifier. And at the same time, in single phase, we have 2 pulses at the output per cycle. In 3-phase, we have 6 pulses per cycle from 0 to 2 pi. So that's another benefit. So this is a kind of a bridge connected to the 3-phase supply over here, a star connection. So 3-phase supply connected to 6 switches over here, and these switches, thyristor switches again. So if we have alpha equal to 0, these thyristor switches are as good as diodes. So, and the load current flows through this load over here, again depending whether pure resistive or inductive. Highly inductive means a large value of L. Okay, so how about the working? First of all, the conditions. So this one, the upper group of thyristors, and then the lower group of thyristors. Upper group of thyristors have T1, T3, and T5. Condition is that they should not work together at the same time. Otherwise, a short circuit will happen. Or even 2 thyristors should not conduct at the same time. Again, short circuit will happen. Second condition, the bottom group T4, T2, T4, and T6 should not conduct simultaneously at the same time, or even 2 of them are also not allowed to work simultaneously. Third condition, T1 and T4, this one, T1 and T4, or T3 and T6, or T5 and T2 should not be allowed to switch together or work together. Again, a short circuit may happen. Now, next condition is that they should trigger at an interval of 120 degrees. As I said, all the 3 phases are 120 degrees apart to cover 360 degrees from 0 to 2 pi. So 120 degree phase difference should be there. So then thyristor pairs, they work in pairs, as we saw in bridge rectifier's case, full wave rectifier's case. T6 and T1, this one, T6 and T1, T1 and T2, T2 and T3, T3 and T4, T4 and T5, T5 and T6. They work in groups, they work in pairs. So we used to have 2 pairs in full wave rectifier, and in 3-phase rectifier, we have 6 pairs. So instead of 2 pairs, we have 6 pairs. So each pair must be triggered at an interval of 60 degrees. So let's say if T6 and T1, which is one pair, is triggered, then the next pair should be triggered only after 60 degrees, not before that. So, and these pairs should be fixed. T6 should be paired with T1, and then T1 should be paired with T2, and T2 should be paired with T3, because in the first cycle, let's say, not in the first instance, this T6 and T1 are conducting. Then T6 goes off, and now T1 is conducting with T2 now. It gets paired with T2. Now T1 goes off because it was already being triggered before. So T1 goes off, T2 is now paired with T3. Now in the next one, T2 goes off and T3 is now paired with T4. And T3 goes off, T2 is now paired with T5. T4 goes off, T5 is now paired with T6. T5 goes off, and now T6 is paired with T1, and so on. The cycle continues only after every 60 degrees of interval and not below that. Okay, now again, as I said, 6 pulses per 360 degrees or per cycle, which is 2 pi. We'll see that now in full wave rectifier, we have 2 pulse frequency per 1 cycle. Here we have 6 pulses per one cycle. So it means the switching frequency is fast. The ripples are reduced, we'll see. But before going into it, you need to remember that how the phasor should look like. Each phase should be 120 degrees apart. These two names, we know that RYB phases are normally the practical approach, and academically we are writing it like VAN, means A is the phase, and B phase, and C phase. And commercially they are called RYB phase. So again, this phase is having a voltage of Vm sin omega t, where Vm is the peak. Now the next phase voltage, phase to neutral, which is Vm sin omega t minus 120 degrees, which is 2 pi by 3. So shifted by 120 degree, and the third one is shifted by minus 240 degree, which comes out to be plus 120 degrees. You can even write minus 240 degrees. Okay. So both of these circuits are equivalent to each other. Only the way of drawing is different. Whichever looks easier for one designer, they choose. So this is the current, load current over here, which is ID over here, DC current at the output, and DC voltage at the output. So again, if you remember the conditions, one thyristor from the upper group and one thyristor from the lower group, they work in pairs. For example, again, T1 and T6 can be one pair, and T1 and T2 can also be another pair, and so on. So depending upon the decision on the pair, the phase voltages are selected. You can see here. So this is for angle alpha equal to 0. So these are the 3-phase input supply. This is Vm sin omega t. An, we saw that. Van is Vm sin omega t. Vbn is displacement by 120 degrees. We'll see that. So this is Vm sin omega t. Vbn is displaced by 120 degrees. And Vcn is another 120 degrees of shift, phase shift. And then the cycle continues again, An, Bn, Cn. So these are 120 degrees phase shift. So over here, we have this pair conducting 6 and 1, T6 and T1 are conducting, and we have VAB at the output. So T1 and T6 are conducting. This one is conducting T1, and all are off. So the current will follow this path. And this is the positive half cycle VAN. This one VAN. So the current starts from here, and this N is now at the lower potential. A is at the higher potential in the positive half cycle. This current continues, IA current continues to flow through this T1 because it is conducting, going through the load from top to bottom again, going here. T2 is off, only T6 is conducting, and now we go here and we come back to this, and now we go back here to the neutral. So it means this current is covering the path from A to B, going from A, starts from A through T1, going to the load from top to bottom, coming back through T6, coming back through B to the neutral. So VAB, now we have covered from A to B, so the voltage developed at the load VD will be across A and B because current has followed this path from A to B, and the voltage developed at the output will be from A to B. So VAB. So we have a voltage at the load which is across A and B, phase A and B. Similarly, when now 6 goes off, now 1 is now having a pair with 2. Again going back, 1 having a pair with 2. Now, this one T1 is now on. It continues to be on from the previous instant. And then the current continues to follow this path from top to bottom and going through T2 and then coming back to this neutral through phase C. So it means now the voltage developed at the load is across A and B, A and C. So the voltage will be across A and C. Similarly, now 1 has been conducting for so long, it goes off. Now 2 has paired with thyristor 3. Now again the same thing. Thyristor 3 is conducting now. So now this phase is positive, phase B. Current follows this path through T3, going through load again from top to bottom, and pairing it with the T2, it will go through the neutral through phase C. So now the voltage at load will be across phase B and C. So VBC will be the voltage at the load due to the conduction of thyristor 2 and thyristor B. And then the cycle continues. Now the thing is that as we saw in the conditions over there, that at every 60 degrees, these thyristors should be turned on, not before that. So pi by 3, which is 60 degrees. So every pi by 3, the new thyristor should be turned on. So it means thyristor T2 is turned on only after pi by 3. Next pi by 3, thyristor 3 is turned on. And then next pi by 3, thyristor 4 is turned on, and so on. So this condition also we have fulfilled. At every 60 degrees, there should be an interval of 60 degrees before we fire a next thyristor. Okay, so this is now the from 0 to 2 pi, we have 6 ripples. Because 6 and 1, now the new cycle starts from 6 and 1. So till 5 and 6, this was one cycle. So in this one cycle, 6 pulses we have received at the output. So now removing these ripples becomes a lot easier. A small capacitive filter can be useful for this because now the ripples are smaller compared to the full wave rectifier where the ripples were larger. So due to this, 3-phase is very much useful because the cost of the circuit will be much lower because we can use very simple filter to to get rid of very small ripples. So this is now the 6-pulse rectifier using 3-phase supply. Next, move forward. Previously we saw the waveforms at angle alpha equal to 0 for 3-phase full wave rectifier. Now let's say we have some firing angle equal to 30 degrees. Now considering T5 and T6 are already conducting from the previous cycle, and now starting from the new cycle, we trigger T1, which is now pairing with T6, as in the previous case with alpha equal to 0. And when T6 is paired with T1, like in the previous case, we have at the load, we have the voltage VAN minus VBN, like in the previous case. This one. VAN going through T1, going back through this load, through T6, and going back to the neutral through phase B. So the current follows this loop from A to B when 6 and 1 are conducting over here. So here 6 and 1 are conducting, it is fixed. So the voltage at the load will be VAN minus VBN, which is this. So VAN minus VBN will be the voltage at the output, which is a shaded part. So this will be received at the output, not the complete path, because due to angle alpha, some part of the voltage pulses will be clipped, as we saw in the full wave rectifier and half wave rectifier, because the thyristor T1 is not conducting till alpha. And in this case, it is pi by 6 plus alpha. And again at pi by 2 plus alpha, which is a 60 degrees of interval, plus alpha, we have a next thyristor triggered, which is T2. Now this T2 is paired with T1. Now these T1 and T2 are now between two phases, which are VAN and VCN, A and C. So VAN minus VCN will be received at the output, at the load. And if we change the value of alpha, this value at the output will be increased or decreased. If we increase value alpha to 60 degrees, now again this wave at the output will be changed. Now in the next instant, after 60 degrees of interval, we fire another thyristor, which is T3, which is now paired with T2, because T1 is off now. So now considering this T2 and T3, which is between phase B and C, they conduct between phase B and C. So VBN minus VCN will be received at the output. The shaded part will be received at the output, and so on. So just by changing the angle alpha, we can change the average output. So just by changing the value of alpha, we can change VAB, which is VAN minus VBN. So thyristors are numbered in fixed order. So in this case, they are numbered in this order: 1, 2, 2, 3, 3, 4, and so on. This we already know, these phase voltages, VAN, VBN, and VCN. Now if we want to find out VAB, which is VAN minus VBN, it's √3 times Vm sine omega t plus 30 degrees. From here we can see that this red vectors in red color show the phase voltages, VA, VB, and VC, as we saw here. VAN, phase A with respect to neutral, phase B with respect to neutral, phase C with respect to neutral. So these are the voltages for all these three phases, 120 degrees apart, which are shown by the red lines over here. And now these three vectors shown in blue are the line voltages, line to line voltages, which is between phase A and phase B, which is called VAB. And then phase B to phase C, which is called VBC. So how we do that? This is phase voltage VA, and this is the phase voltage VB projected backwards in the negative direction, which is minus VB. And now taking the resultant between VA and minus VB will give us VAB. And we see that VA minus VB will give us VAB. So if we take the resultant, which comes out to be √3 times of this one. So that's why we say √3 times. And the displacement is 30 degrees. So if we take the resultant between VA and minus VB and find out the resultant vector over here, it is shifted by 30 degrees. So a shift by 30 degrees. And in between all phases, which are shown by a red line, we have 120 degrees of phase shift. So all these three red lines are 120 degrees apart. So just using this phasor, you can find out the resultant. So all the line-to-line voltages are now √3 times of the phase voltage shifted by 30 degrees. As we can see from here also, shifted by 30 degrees, and the magnitude is √3 times of the phase voltage. So now if we want to derive the DC voltage, which we already have done for the half-wave rectifier or full-wave rectifier. So if we want to do it for the three-phase rectifier also. And we know that we have 6 pulses in one cycle, which is 0 to 2 pi. And we know that the DC voltage at the output, we have 6 pulses per complete cycle, 2 pi. And the output voltage we need to integrate from 30 plus alpha, because the first crossover happens at 30 degrees. The first phase crossovers, the two phases, they cross each other at 30 degrees. So 30 plus alpha. Only starting from the first crossover of two phases, we calculate alpha. So 30 plus alpha till 90 plus alpha, because we need to meet the condition that the interval should be 60 degrees. In full wave rectifier, the interval was 180 degrees. Here the interval should be 60 degrees before the next group of or next pair of thyristors is triggered. So from 30 plus alpha to 90 plus alpha, we integrate the voltage, which is √3 Vm sine omega t plus 30 degrees, which we saw in the previous slide. Integrate this, we get the DC voltage, which depends on the parameter cos alpha. This √3 Vm can be also denoted by VML, which is line-to-line maximum voltage. This one Vm was maximum phase voltage. This is VML is maximum line-to-line voltage. And then putting different values of alpha, we can have a different values of DC voltage at the output. Normalized voltage also we can do just by calculating the maximum voltage for angle alpha is equal to 0. Putting it over here, DC over dm, we have a normalized average output. Okay, now after this DC voltage or average voltage at the output, we can also find out the RMS voltage at the output. Similarly, just using the same conditions, 30 plus alpha to 90 plus alpha, 6 pulses per one cycle, 2 pi, taking the square of the voltage, and now 2 pi is the, dividing it by 2 pi is the mean, and then making a square root, we get the RMS. And from this RMS voltage, we can also find out the RMS current. Similarly, we can also find out RMS power or average power at the output. So with this, we finish the AC to DC converters. And in the next chapter, we'll start with the DC to DC converters. Okay, thank you.